Now I will present a special fixed point iteration which is called the Newton-Raphson method. So the Newton-Raphson method is a fast fixed point iteration. The convergence is quadratic. We will explain hereafter and prove the quadratic convergence of this algorithm. So the Newton-Raphson method, basically the solution at step n+1 is constructed as xn, where xn is the solution at step n, minus f of xn over f prime of xn. So it's a fixed point iteration method with g of x being equal to x minus f of x over f prime of x. So now I will show you geometrically how the Newton-Raphson method works. So we start by point x0, which is the initial solution. We take the tangent at this point x0. So this would give me x1, the solution at the next step. And then I repeat the process. I take the tangent at the point x1. It will give me x2. The intersection with the x-axis will give me the point x2, and etc. So now we will derive this Newton-Raphson formula. As we said, at the step n+1, the solution at step n+1 is constructed as being the intersection of the line tangent to the point xn f of xn and the intersection of this line with the x-axis. So first let's construct the equation of the line. So the equation of the line is given by y of x is equal to f prime of xn x plus b. Now if you take y of xn is equal to f of xn, then you get y of x is equal to f of xn plus f prime of xn x minus xn. So by the way, this is the Taylor expansion of the function f of x around the point xn. Okay, so now xn plus 1 is given by the intersection of this line with the x-axis. Then y of xn plus 1 is equal to 0. Then we get the point xn plus 1 is equal to xn minus f of xn over f prime of xn. We get the Newton-Raphson formula. Now we will analyze the convergence of the Newton-Raphson method close to the solution. So for any fixed point iteration method, xn plus 1 minus s, means this is the error at the step n plus 1, is equal to g of xn minus g of s. Now if I express g of x around the point s as being, taking the Taylor development of g of x, so g of x is equal to g of s plus g prime of s x minus s plus g plus 1/2 g secant of x x minus s square, etc. Now you evaluate this Taylor development at the point xn. So you get, for the difference of g of xn minus g of s, you get g prime of s xn minus s, this is the error at step n, plus 1/2 g secant of s xn minus s square plus higher order term. Now for the Newton method, g of x, as we said, is equal to x minus f of x over f prime of x. Now, if I develop this g prime of x, so g prime of x becomes 1 minus f prime square minus f secant over f prime square. So we did here u v prime minus u prime v minus u v prime over v square. So we get at the end, when we express the common denominator here, we get f of x multiplied by f secant of x over f prime square. So this is for the g prime of x. Now, in order, of course, to ensure the convergence of the algorithm, the Newton method being a fixed point iteration method, so this g prime of x in absolute value must be inferior or equal to 1. Now, because S is the solution, g prime of S is equal 0 because f of S is equal 0. Now, if I express the g secant, I get this expression, and if I express this expression at the point S, so all the term containing f here, because f of s is 0, will disappear. So these two terms will disappear. So this only term will remain here. And so I will have g secant of s is equal f secant of s over f prime of s. So the error now at the step n plus 1, of course, if we are around the solution S here, okay, because this term now has disappeared, only remain this term. So we have the error at the step n plus 1 is equal to 1/2 f secant of s over f prime of s, the error at the step n square. So if this quantity 1/2 f secant of s over f prime of s is inferior to 1, we said that the Newton is of quadratic convergence. This means that the error at step n plus 1 would be inferior or equal to the square of the error at step n. So this method will converge very fast, because, for example, if we have an error of 10 minus 2 at the step n, then we will have an error of 10 minus 4 at the step n plus 1, an error of 10 minus 8 at the step n plus 2, etc. So the Newton method around the solution S converge very fast if we have quadratic convergence. 1/2 f secant of s over f prime of s is inferior to 1. So if we have this property, then we say that the Newton is of quadratic convergence. Now, the Newton method may diverge in some cases, especially when the point x0 or the initial estimate is badly chosen. So consider, for example, that we have a function f of x, such f of x is tangent to the y-axis when x becomes close to 0. So in this case, if I choose x0 in this position here, then when I construct the x1, as you see that the x1 is far away from the solution, and additionally you cannot even construct here the function g of x, because f of x1 is not defined at this point. So if you choose x0 at this initial value, the algorithm will diverge and will not lead to the solution. Now, if we choose x0 at this point, then when we construct the x1, we are close to the solution, and if we repeat further the process, it will lead to the solution. So the choice of x0, or the initial estimate, determine whether the algorithm converges or not. So a criterion for the choice of x0 is first to choose x0 close enough to the solution. This means that the interval AB must be small enough. And second is to choose f of x0, to choose x0 such as f of x0, f secant of x0 is positive. So with a choice of x0 respecting these conditions, the algorithm should normally converge. Now, as a task, I will ask you to do the same task as the task 3, but this time using the Newton-Raphson formula. So instead, you will replace the function g of x, instead of minus exponential minus x that we used for the fixed point iteration, you will use here the Newton-Raphson formula. And so you will replace g of x by x minus f of x over f prime of x. Of course, you will use the analytical formula for f prime of x and f of x in this case. And then you will count the number of iteration, and you will compare to the previous program. And you will see that in this case, the Newton-Raphson formula will be much faster. So basically in 4 iteration, it will lead to convergence with a precision of 10⁻⁶. And now I will present the secant method. So the secant method is similar to the Newton method, and it can be seen as an approximation to the Newton method, even though it was developed independently from the Newton method, and it's much more ancient compared to the Newton method. Now, remember the Newton method. So for constructing the first point, we were taking the line that is tangent to the function at the point x0. The secant method constructs an approximation to the tangent at the point x0. So instead of starting with one point x0, we start by choosing 2 points x0 and x1 that are close enough to each other, and we construct the line passing to the points x0 and x1, and we search for the intersection of this line with the x-axis. So this line is the approximation for the tangent at the point x0 or x1 if x0 and x1 are close enough to each others. And then I get the point x2. And now I construct the line passing to the points x1 and x2 to get the new solution x3. Okay, so the solution x3 would be the intersection of the line passing to the points x1 and x2. So this is the solution at the second step. And then for the solution at the fourth step, I consider the points here x2 and x3, and I get the x4, which, as you can see here, is very close to the solution. And now I will derive the expression for the secant method. So in the secant method, we construct the solution at the step n+1, the point xn+1, as the intersection of the line passing through the point xn and xn-1 with the x-axis. So first let's get the expression for the line passing through the points xn and xn-1. So we are searching for a line of the expression y of x is equal a0 plus a1x, and y of xn is equal to f of xn, y of xn minus 1 is equal to fx minus 1. So we get the expression for a1 and a0 as we did for the false point iteration method. And now finally the point xn+1 is taken as the intersection of this line with the x-axis, and so xn+1 is minus a0 over a1, so it's equal to xn minus 1 f of xn minus xn f of xn minus 1 divided by f of xn minus f of xn minus 1. Now, as you can see, the secant method is very similar to the false point position. So at every time we are searching for the intersection between the line passing to 2 points and the x-axis. But the difference between the secant method and the false point position is that in the secant method we choose the points x0 and x1 not as the extrema value of the interval a and b, but 2 points that are close to each other, so it's can be seen as an approximation to the Newton method, while in the false point position we were choosing the points x0 and x1 as being the border of the interval and reducing the interval consequently. So the two methods are different, even if they are quite similar, and when we are close to the solution they should converge the same. Now, as I said, the secant method can be seen as an approximation of the Newton-Raphson method, and I will prove that. So let's consider first the expression for the Newton-Raphson iteration. Xn+1 is equal to xn minus f of xn divided by f prime of xn. Now if we approximate the derivative at the point xn by f prime of xn is approximately equal to f of xn minus f of xn minus 1 divided by xn minus xn minus 1, which is the slope of the line passing through xn and xn minus 1. Okay, so this is also called the finite difference approximation of f prime. So now replacing into the Newton formula, then you get the approximation for the secant method. Now the advantage of the secant method compared to the Newton method is that it doesn't require the evaluation of the derivative. So it can be interesting in cases where the analytical expression for the derivative of some function cannot be evaluated, but it is relatively slower than the Newton method. The convergence rate is approximately equal, but it is approximately quadratic, but not exactly quadratic. So the order of convergence is between 1 and 2, is around 1.6. It's not exactly a quadratic convergence. Now, as a task, I will ask you to draw the flowchart for the secant methods and to solve the same problem as task 3, but this time using the secant method, and you will count the number of iterations and compare with the previous program. Now, as a starting point, you will have to start from 2 points here, x0 and x1, and save at each iteration the solution of the 2 previous iterations. And now, as a summary of this chapter, we will recall the pros and cons of the different methods. So the bisection method is the most basic root searching method. The convergence is slow, but the principal advantage is that there is no specific conditions of convergence. So the algorithm, the bisection algorithm, will converge no matter what is the function f of x or the interval a and b, if a solution exists in this interval ab. The false position method is in general faster than the bisection, but it's slower than the Newton method. And the principal advantage also is that there is no specific condition of convergence, because it is similar to the bisection method, because we are reducing the interval a and b further and further. Now the Newton method is a very fast convergence method. So the order of convergence is 2 when close to the solution, but the major drawback is that it can diverge in some cases, and it requires also the evaluation of the derivative of the function. So we need to have the analytical expression for the derivative of the function for which we are searching the root. Now the secant method can be seen as an approximation of the Newton method. So the order of convergence is approximately quadratic, not exactly quadratic. It's a little bit slower than the Newton method. But the advantage is that it doesn't require the evaluation of the derivative of the function. Now, the major drawback of the secant method is similar to the Newton, because it can diverge in some cases as the Newton.